Hi everyone. Thank you for watching my previous video on introduction to Z transform. Now I have received some queries, some questions regarding Z transform and regarding transforms. So before going ahead, I would like to answer the questions which I have received from your end. So these are the following questions which I will try to address today. The number one question which is raised is, what is a transform, or what do you mean by a transform? This is the question asked. So I shall answer this question. Second question which is asked is, why do we transform a signal? Why do we transform transform a signal? And the next question asked is, which are the other transforms? Others means other than Z transform. Which are the other transforms? And last question which is asked is, how many transforms are possible? How many transforms are available? So these are the questions asked, and I will try to answer this one by one. So, first question first. Now, what is a transform? So, transform is another way of expressing a given signal. So, I can say expressing a signal in terms of a set of other signals. This expression or this way of representing a signal in terms of set of other signals is called transform. And this set of other signal, this is very important, this set of other signals, this set of other signal is called the set of other signal. Other signal means the signals in terms of which a given signal is expressed. This is called basis. What it is called? Basis. So now, what is the definition of transform? Express a signal in terms of basis functions or basis sequences. If you are working in continuous time domain, then this basis would be a set of continuous time functions. And if you are dealing with a discrete time system, or if you are working in a discrete time domain, then this set of signals or this basis would be set of discrete time sequences. So I can say this basis could be what? It could be a set of continuous time function or it may be set of discrete time sequences or discrete time signals. Now, this basis term is borrowed from linear algebra, and I have given you the crude definition of basis. So, I will try to explain in little more detail what do you mean by basis. So, what is the basis? Basis is a set of vectors, or I can say set of linearly independent vectors that span that spans the given space. So this is a mathematical definition of basis. Basis is a set of linearly independent vectors that span the space. Now there is coming a term linearly independent. So we shall see what do you mean by linearly independent vectors. And here the vectors could be set of continuous time functions, or these vectors could be set of discrete time signals. So what do you mean by linearly independent vector? So what is linear independence? A set of vectors, let this set to be v1, v2, v3 and so on. Assume there are n vectors. So this set of vector is linearly independent if and only if the combination that gives the zero vector, I represent zero vector by 0 under arrow. So that gives the zero vector is 0v1 plus 0v2 plus 0v3 and so on 0vn. So only this combination where all the coefficients of v1, v2, v3 and vn are 0, only this combination produces 0 vector. Then this set of vectors, this set of n vector is linearly independent. Or in other words, the linear combination x1 v1 plus x2 v2 so on xn vn is equal to zero vector only when all x are 0, then the set of vector, this implies the set of vectors is linearly independent. But if you get zero vector for some other combination where all x are not zero, then this set of vectors v1, v2 up to vn will be called linearly dependent set of vectors. So linearly dependence means when all x are not zero and we get for some combination x1 v1 plus x2 v2 plus so on xn vn equals a zero vector. Now remember here this x1 x2 x3 this x are either real numbers or they are either complex number, and this v1 v2 vn, they are not numbers, they are vectors. And as I have said, these vectors could be functions or this vector could be sequence. So if you have some combination where all x are not zero, and if that combination produces zero vector, then the vectors are linearly dependent. So we saw the basis, definition of basis, and there we saw that basis is what? Basis is a set of linearly independent vectors that span the space. So the meaning of linearly independent vector is clear to us. But what do you mean by spanning the space? So I will now try to clarify what is meant by spanning the space. So if any vector in a given space can be expressed in terms of vectors v1, v2 up to vn, then we say that the set of vectors v1, v2 and so on vn spans the space. Or in other words, we can say the set of vectors v1, v2 and so on vn spans the space if their combination, if their linear combination, if their linear combinations fill the whole space. Now here a new term has been introduced, linear combination. So now first we will look at what is meant by linear combination, and then we will again see the definition of basis in totality. So linear combination. Let's say you have two vectors x and y. These are the two vectors in given space. Then if you multiply these vectors by some constant or some scalars alpha and beta, where this alpha and beta may belong to set of real number, or they may belong to set of complex number. So first what we have done, we have multiplied the vectors by alpha and beta, where alpha and beta are real or complex scalar, and if we add and get a new vector. So this is a new vector, and this new vector alpha times x plus beta times y, this is called linear combination of x and y. This is what? This is linear combination of vectors x and y. So we saw the definition of spanning the space, or what do you mean by the set of vector spans the space? The set of vectors v1, v2 spans the space if their linear combination fill the whole space. For example, you have, let's say, three-dimensional space. All you are aware of this three-dimensional space. This is a three-dimensional space. And you might be knowing these unit vectors I, j, and k. So let's say the I, j, k are some vectors I, j, and k. So these are three vectors. Now this set of vectors, the set of vectors I, j, k spans this three-dimensional space. It means if you take any point in this three-dimensional space, let's say the point is P. This is the point P. Now this point P can be expressed in terms of these three vectors. So Pi can expressed as alpha I plus beta j plus gamma k, where this alpha, beta, and gamma, these are some scalars, whereas ijk are vectors. So here there is no, there is, so let me remove this bar from gamma. This is simply what? It is simply gamma. Gamma is the scalar. So k is the vector. So this three vectors fills the whole space. If you take all possible combinations of these three vectors, those combination will fill this three-dimensional space, or any point in this three-dimensional space can be expressed in the terms of these three vectors I, j, k. Therefore, this set of vector spans this three-dimensional space. And we saw the linearly independent vectors. We know that alpha times I plus beta times j plus gamma times k, this combination would be zero vector only when alpha, beta, gamma, all three are zero. So this I, j, k are not only spanning this three-dimensional space, they are also linearly independent. So we can see that this set of vectors I, j, k, it is a set of linearly independent vectors that span the 3D space, three-dimensional space, and therefore I can say that this ijk forms a basis for three-dimensional space. So the question asks what is a transform? And the answer is expressing a signal in terms of some basis. This is called transform. Now, the next question asked is why do we transform a signal? So the next, I will answer the next question now. So I hope the first question is clear. The first query is clear now. What is a transform? Transform is expressing a signal in terms of set of some other signals. This set of other signals is called basis. So expressing a signal in terms of various different bases is called transform. The second question asked is why do we transform a signal? Why do we transform a signal? So, what could be the answer of this? The most general answer which I can give is the transforms are taken because they make our lives simple and comfortable. So the answer is transforms in order. Why we take transform? In order to make our lives simple and comfortable. But this is not completely explaining, completely understandable. What does it mean that transform makes our lives simple and comfortable? What does it mean? So, if you recollect your school days, what did you do for multiplication and division of long numbers without the help of calculator or any other calculating device? What did you do? You use log tables. So log tables or logs or anti-logs had been used by you for multiplying or dividing the numbers when you do not have any computational device. So logs and anti-logs helps you in multiplying and dividing the number. Now, why do we take log or why do we take anti-log? So now if you want to multiply, let's say, why log and anti-log? Now if you want to multiply two numbers and the multiplication is difficult, if the numbers are very long, then you take what? You take their log. And this log converts or transforms into what? Log of A plus log of B. So the multiplication has been transformed into what? Addition. Similarly, if there is a division of two numbers, then you have log of A and log of, and there would be what? Subtraction. So log of A minus log of B. Now the base could be anything. It could be E or it could be 10. So why do we take logs? The log has converted the operation of multiplication into the operation of addition, or the operation of division has been converted into the operation of subtraction. And we know the operation of addition and subtraction are simpler than the operation of multiplication and division. So taking a log helps us in what? In converting complex multiplication and division operations in simpler addition and subtraction operation. Now after adding their logs, if you add logs and if you take anti-logs, it gives you the final result. So taking logs are like taking the transform of numbers, and taking anti-logs means what? Taking inverse transform on the numbers. So log is like a transform performed on numbers, and anti-log is like an inverse transform performed on the numbers. So logs and anti-logs are used for simplifying the computation performed on numbers. Similarly, now I will address why to transform signals. How transform will make our lives simple or comfortable. That now we will see. So how transform makes our life simple and comfortable when we take the transform for the signal. So the answer is as follows. There are many reasons. The first reason is taking the transforms gives simpler analysis. The first reason is simpler analysis of LTI system. LTI stands for linear time invariant system. I am sorry, in the last lecture I said linear time system. LTI means linear time invariant system. So when you take transforms of the signal, the analysis of linear time invariant system becomes simpler. So how the analysis becomes simpler when we take transform? So if you consider a LTI system, let's say this box represents a LTI system. This is an LTI system. And let's say the impulse response of this LTI system is h of n, and input applied to the system is x of n, and the output of this system is y of n. And I am saying when we take transforms like Fourier transform or Z transform or Laplace transform, the analysis of LTI system becomes simpler. But the first question is, what do you mean by analysis? Then I will show how it simplifies the analysis. What is meant by this term analysis? So analysis means what? To find or to compute rather output of a system for the given input. When the system has been expressed or represented in terms of some mathematical model, means you are not given the actual system. What you are given? You are given some mathematical model of the system, and you are given the input, and you are asked to compute the output. So this process of computing the output for the given mathematical model of the system is called analysis. Now, this mathematical model can be given in various forms, in various ways. The mathematical model can be given in the form of input-output relationship. For example, let's say you have some input-output relationship yn equals x of n minus n. This represents what? This represents a unit delay system. This is a unit delay system. And this unit delay system has been expressed in terms of this input output relationship. In general, this input output relationship can be expressed in form of a difference equation, or it can be expressed in a form of differential equation if the system is continuous time. So for example, yn equals 2 times yn minus 2 plus 3 times yn minus 1 plus xn. Here you see the system has been expressed as a difference, linear difference equation. And if, let's say, one more example for continuous time system where yt is, let's say, 2 d2y dt squared plus 4 dy by dt plus xt. Here system is expressed in terms of a differential equation. So these are the mathematical models for the system. And in my previous slide, I expressed system with the box, and within the box, I wrote Hn. So sometimes, especially for linear time invariant system, the mathematical model can also be given. This model can be given in terms of the impulse response of the system, impulse response, or step response, or in terms of transfer function or system function. So now how I can explain the analysis of the system? The analysis of the system means to compute the output for the given input when the system is expressed either as a difference equation or as a differential equation, or in the form of impulse response, or in the form of step response, or in the form of transfer function or system function. So this is called analysis for given input and given mathematical model of the system to compute the output. And now I am saying that when we take the transforms, this analysis becomes simpler. How it becomes simpler? You might be knowing for LTI system, if the impulse response is known, let's say this is an LTI system with impulse response Hn, input Xn, and output Yn. Then how these three X, H and Y are related? We know this Yn equals what? Xn convolution Hn. And you know this convolution is a complex operation. It is not as simple as multiplication or addition of sequences. It is little more difficult than addition or multiplication. So to analyze the system in time domain requires computation of what? Computation of convolution. And this convolution is a complex operation. For example, we just took example of unit delay system. So for the unit delay system, impulse response can be given by delta n minus 1. This is the impulse response of unit delay system. And now if I give you a sequence, let's say xn is the following sequence. It is 1 at 0, it is 2 at 1, and it is, let's say, 3 at 2, and it is 0 elsewhere. This is the sequence x of n, and this is the impulse response h of n. And if I ask you to find the output yn, if this input is applied to this unit delay system, then you can say this yn will be what? Xn convolution hn, and hn is what? Delta n minus 1, and this will gives you what? Xn minus 1. So what did you do to obtain the output? You perform the convolution. But here the system was very simple, a unit delay system. But if I make a system little more complex, even though the system is LTI system, then the computation of this convolution will become difficult. And therefore, the transform may come to our rescue. Now, if you take the transforms of these three signals, assume you take Z transform. Let's say Z transform of Xn is X of Z. Z transform of Hn is, let's say, H of Z, and Z transform of Yn, let it be Y of Z. Then in time domain, Y, X and H are related through convolution. How they would be related in Z domain? This YZ would be XZ into HZ. So what is important to notice? That the convolution operation in time domain has been transformed into multiplication operation in Z domain. And naturally, the operation of multiplication is simpler than the operation of convolution. So, if we can find YZ, then having obtained YZ, Yn can obtain by taking inverse Z transform. And this is the easier way of analyzing the system. So this is the first reason of using transform. Second reason of using transform is the following. Second reason is manifestation of hidden properties of the signal. This is the another important reason. Now some properties or some characteristics of signals may not be obvious or may not be clear in the original domain. Let's say original domain is time domain. So the some property may not be obvious or they may be hidden in its original domain. But these properties may manifest well when signal is transformed into the other domain. This is very much possible. For example, if I give you some signal in time domain, let's say the original domain is what? Time domain. This is the signal. It is given in the time domain. Or you are looking this signal at CRO, cathode ray oscilloscope. And if somebody asks you what is the bandwidth of the signal, then it would be very difficult for you to answer about the bandwidth of the signal just looking at the time domain representation of the signal. However, if you take its Fourier transform, that is, if you transform the signal in the frequency domain, then it is possible to answer the bandwidth about the signal. So instead of CRO, then you can use a spectrum analyzer. A spectrum analyzer computes the Fourier transform of the signal, and using the Fourier transform, it is easier or it is simple to give the answer about the bandwidth of the signal. So there could be several other properties. I have given a simple example that some of the properties of the signal may not be clear or obvious in the original domain, but when we transform the signal in some other domain, those properties may be obvious or may become clear or may become distinguishable. So therefore, when we take the transform of the signal, some hidden properties may manifest very well. This is the second reason. And the third reason, which is very important, it is compact representation of the signal. Third reason is compact representation. Now, what do you mean by the compact representation? Now, to represent the signal, we need some values or we need some coefficients. The values of the coefficients which are required to represent a signal in different domain varies. On transforming a signal into a suitable domain may lead to a compact representation of the signal. Means when we take the transform of the signal, it is possible that the number of coefficient required or the number of values required to represent the signal are lesser. So we need, it is very much possible, we need lesser number of values or lesser number of coefficients to represent the signal in the transformed domain. I give you an example, a wavelength transform. It gives the compact representation, and because of the compact representation, there is a process called compression. We can achieve some compression using some, if when we transform a signal in some other domain. So wavelength transform is a good example, and it is very much suitable for the compact representation of images. So what will happen when we take some suitable transform, most of the energy, most of the energy of the signal will be concentrated only in fewer transform coefficients. So the energy would be concentrated only in fewer number of coefficient when we go in transform domain. So this is the reason of using transform. I think I should stop here. Remaining two questions I will answer in my next video. Thank you very much.